Good morning again. So this is the last lecture in MECH 520. Where is the yay? Okay. So what we'll do today is I'll just go, since you are not going to get these assignments back, and also as preparation. I want to go over all the questions and explain which was the right way to answer it, and the grades will be posted in a couple of days on these assignments. But it's more important to understand from the way the question should be answered how you should answer them on the exam. Yes.
Where are grades being posted? Because I haven't been able to see mine.
Connect. I never looked because I just post them there. But students tell me they can see them right away on Connect when I post them. So ask somebody how they see it. I don't know. I just know how to post them. Anyway, don't worry. You can figure it out after the lecture. But okay. So as I said, this will be 10% of your grade, and the final exam is 60% of your grade, just like on the trial exam. Okay. So when you see the grade on the final exam, it will be in points out of 60, and then you'll see the final grade for the term. So first we'll go over what I expected as good answers, and then we'll continue with system design. Okay? So assignment. Okay. So the first question is, why is it harder to build a good actuator than a good sensor? Assignment. Okay, good. So, why is it harder to build a good actuator than a good sensor? So, the main reason for that is an actuator has to produce power. So, to produce power, you're dealing with bigger forces, you're dealing with heating, you're dealing with all kinds of time delays because you have big coils. Now, a sensor, it just has to sense something. So in theory, there is no power dissipated in a sensor. Things can be very small. There's no heating issues. There's no current issues. So you don't have all the constraints. Now the main reason is this issue to do with time delay. Because when you have to produce current, you have to move things, then you have assignment. When you have to deal with an actuator, you have to deal with some inevitable time delays, because if you have, as I showed many times, you have a coil, you have an electrical time delay, a mechanical time delay. So all these time delays cause a problem in servo systems, because all the time delays become phase shift. And if you have a phase shift in the servo system, that's basically the limitation. All goes back to Nyquist criteria. If the gain is more than 1, phase shift 180 degrees, you cannot stabilize the servo. Now, because in a sensor there are no time delays, or things which move are photons or electrons, there's very little time delay, then the sensors don't cause phase shift. So this question is in the contents of servo systems. If you didn't need to close the loop, it's easy to build an actuator, it's easy to build a sensor. But if you're talking about a sensor or an actuator for a servo system, it's different, because then this time delay becomes dominant. And in a sensor, it's much easier to build a sensor because it has very few moving parts, very small parts, or no moving parts. It's much easier to build a sensor with no time delay. So in a nutshell, the answer is two things: time delay and power dissipation. Because usually actuators, because they have to do work, there's always issues of heating, steady state limit, pulse limit. All these things don't exist in sensors. So I think that's an obvious question. Okay. Now, what does the term characteristic impedance mean? And list two advantages of a transmission line over a regular cable. So, characteristic impedance is a property of a transmission line. And what it means is it's an impedance that is inherent in the structure of the transmission line. If you terminate a transmission line by its characteristic impedance, and if you drive it by the same impedance, you drive it from a source which has characteristic impedance, you have two advantages. First, the amplitude doesn't vary with frequency. And the second advantage is you don't get reflections, because when you send a pulse you don't get electrical reflections. There's many other advantages, but if I had to list the two biggest ones, so if I have a transmission line, and a coaxial cable is just one example, it's not the only transmission line, but a coaxial cable, like say the coax you have in the lab, which says on it 50 ohm. Okay? If you look at the coaxes you use in the lab, there is little letters printed on them. It'll typically say on the coax RG62 or whatever, or RG174. On the thinner cables it will say RG174, which is just a type of the cable, 50 ohm. So this coaxial cable you have in the lab, that's a transmission line. So if you terminate it by the number which says here, if you terminate it to ground by 50 ohm, and when you drive it, you also drive it by 50 ohm from a source which is considered a perfect source with no impedance. When you do that, both the body plot, amplitude versus frequency, the body plot is flat, and it only will start rolling off at very, very high frequencies, like hundreds of megahertz. So for every practical purpose, the capacitance inside that line, because of course inside that line it behaves as if it has capacitance and inductance, whatever happens inside that line, no matter how long it is, will not cause the frequency to roll off. Okay? And the second advantage of this, if you send a sharp pulse, and the pulse propagates, when it comes here, it gets absorbed without any reflection. If it wasn't terminated by the right impedance, the pulse will get reflected back and come back. And then you'll get, instead of a nice pulse, you will get something like this, which is made up of different reflections. Okay? Now, whether these reflections will be distinct or whether these reflections will just add up and distort the pulse has to do with the width of the pulse compared to the transit time. Right? Because to get a reflection, something has to travel the whole length and come back. So if this is L, the transit time is L over C. C is the speed of light. Okay? So say if this was say 3 meter, okay, it will be about 10 nanoseconds. The transit time, this is C is actually the speed of the light in the coax, which is less than the speed of the light in air. I explained this when we talked about transmission lines. It's not so important for now. But just to be a perfectionist, you have to remember that inside a material, the light travels slower than in air. So the speed of light inside a cable is about 2/3 speed of light. But that's not important. That is the speed of light in the medium, and it's same as in glass, in air, in optics. When the light goes through glass, it's slower. If you really want to kind of be picky, if you know the epsilon and mu 0, you can calculate the speed of the light in the medium, which is square root 1 over mu epsilon. But basically, you can estimate this. Let's say it's 10 nanoseconds. So if the pulse is 1 nanosecond, and it takes 10 nanoseconds to come and 10 nanoseconds to go, you will see the reflection distinct. The pulse is coming, and 20 nanoseconds later you see some reflection. If the pulse is 100 nanoseconds and the transit times are 10 nanoseconds, you'll see this. Within the 100 nanoseconds, you already get some reflections which will distort it. But bottom line, if you have a transmission line, you eliminate reflections and eliminate roll-off. Roll-off is thing with the amplitude changes with frequency. Or eliminate frequency dependence. Okay, so characteristic impedance is the natural impedance of the line to electromagnetic waves, okay, which depends on the construction of the line, and when driven by that impedance and matched by that impedance, the response is invariable with frequency and you don't get reflections. Okay? And this is actually the reason you drive it from this end, from 50 ohm, because if you get a small reflection here, you also don't want to get reflections of reflections, because if a reflection comes back here and this is driven, say, from 1 ohm, you'll get a reflection here too. So this only works if it's loaded by the characteristic impedance and driven by the characteristic impedance. Now, in a more fundamental level, the reason this has to be like this is in the Heaviside proof, which I just gave you the highlights of the Heaviside proof. The whole concept of transmission line only exists if it's infinite. And the way you make it look infinite is, if this is 50 ohm and you add 50 ohm and you drive for 50 ohm, it is just like one section of an infinite 50 ohm line. So the whole proof of Heaviside theory about transmission lines relies on the line being infinite, so it has to be at both ends connected to something which looks exactly like this. Because as you remember, the Heaviside proof, the proof was based on adding a section of delta L and showing its invariant and then taking the section out. Okay, but that, you don't have to remember that. Okay, so this is a transmission line. Question number 3, which electromagnetic actuator cannot be damaged by momentary overdrive and which has the best linearity? So this all of you know. If it has no magnets, it cannot be damaged by momentary overdrive. It can only be damaged by heat. And momentary means quick, there's no heat. So any moving iron cannot be damaged by quick overdrive. And best linearity is usually moving coil. Now we know moving iron is non-linear by definition, because when you derive the equations, it's already non-linear. Moving magnet can be made linear. Usually moving magnets have a small magnet and a big coil, because you want the moving part to be light. And if you have a small magnet and a big coil, the big field of the coil can a bit distort the field of the magnet, so it can be a bit less linear. But moving coil usually has a big magnet and a small coil, so you can assume that B is constant. Is that explanation clear? Okay? Because we always assume B is constant. We said BLI, BLB, but there is some interaction. If you have a B, if you have a coil, say, if you have some coil like in a motor, okay, and you have an armature here, and this is a permanent magnet, let's say NS, so which creates some B. Now, this coil creates some magnetic field which tries to distort the existing field. So as long as the coil is small and this magnet is big, we assume B is constant, everything will be linear. Okay? But if this coil is big and this magnet is small, say if you used it the other way as a moving magnet, you'll put the coil here, and you put a little moving magnet inside. That field of the coil can be much bigger than the field of the little magnet and distort it, so it will be less linear. That phenomena that the magnetic field caused by the current distorts the existing magnetic field, this is known in the general name armature reaction. I'm not sure I even mentioned that, but in motors at least it's called. We didn't get into it because it's not so important for you, but there is this phenomena especially in motors, where you drive a big current into the armature, and it distorts the whole magnetic field. So the magnetic field is no longer like this, but the magnetic field now starts looking like this. So the commutation isn't perfect. All kinds of things are not perfect. There is some solutions to that. We didn't get into that in this course. But in any actuator, there's a bit of that. So if the magnet is very small, the coil is very big, the coil can distort the whole magnetic field of the magnet. So because of that, a moving coil actuator is a bit more linear, because you can make a stationary magnet, which can be very big. It doesn't have to move. Okay. Number 3. Which sensor is preferred for sensitive measurements? AC output or DC output? Assuming everything else being the same. So you know the answer, of course. It's always AC output, because when you talk about sensitive measurements, you always talk about a lot of gain. To do a sensitive measurement, you need a big amplifier. Now, every amplifier has some DC offset. Like an op-amp has a spec, input offset voltage, input offset current. So any amplifier has offset, which means the output drifts a bit. So if your measured quantity is DC and the output has some DC offsets, then it's hard to separate the measured quantity from the drift. Now offsets can also occur because you have in the input you can have like electrolytic action, basically battery action, you can have thermoelectric action. Let's say you have a couple of wires of different metals, you have a thermoelectric effect. So there is many reasons why you can generate a DC voltage. There's many reasons why you can have a DC voltage generated in an input. Yeah. So because of that, when you amplify DC, it's hard to separate your signal from all the DCs which are created because of offset, electrochemical, thermoelectric, and so on. So that's why if you can have something which is inherently AC, all what you need is, as a minimal, is just AC couple it with a capacitor. All the DC drifts cannot go through. Okay, let's say LVDT. If you take an LVDT and run it to an amplifier, you can immediately AC couple it. And in any case, even if it's not AC coupled, the output of the amplifier can be AC coupled, where your signal is AC. Okay? Good. That's why, for example, in a capacitive sensor, you can build sensors like this which go down to atomic measurements because it's all AC. And you can have a frequency, a constant frequency, and you can filter just this frequency out. So all the noise, not just the DC, but other noises, don't get through. And we even spoke about the spectrum of the signal. If you remember, the signal, when you have an AC output sensor, the spectrum of the signal is not a single spectral line. Now if your sensor works at frequency Fc, the spectrum, meaning this is amplitude and this is frequency, the spectrum doesn't look like this, but actually has side bands because the amplitude is changing. If say LVDT is moving, the amplitude is changing, so the output of an LVDT looks like this, and this is a change in the LVDT position, so the signal looks like an AM signal, and we spent enough time on that, and because of that the spectrum looks like this, so the filter cannot be zero width but can be very narrow. So all the noise is stopped. Noise and DC drifts. If you didn't understand what I just said, you're in bad shape. You should refresh this chapter. Okay, now, when tracking a light spot with a camera like a webcam, which spot will give best resolution, a small or large? Assuming it's a binary camera. So we went in great detail through that. So, contrary to initial intuition, which says maybe a small spot will give better resolution, the answer is if you have a camera and you want to track the movement of a spot, the best thing is to have a big spot, because when it moves, it maximizes the number of pixels which change. And because of that, you can also interpolate, because the movement could be 1 pixel, but because we have hundreds of pixels changing and not all of them change at the same time, it means you can interpolate to a much smaller movement than 1 pixel. And remember the example I gave you. So I gave you the example, if you have a slanted line like this, you have a grid of a camera and you have a slanted line. This is black and this is white. So as the slanted line moves 1 pixel, assuming the slant is 1 row, as the slanted line moves 1 pixel, the number of pixels which change is the number of pixels in a row. But for each fraction of a pixel, 1 more pixel will turn on. So if this is 1,000 pixels, it will actually detect movements of 1,000th of 1 pixel, because first this will turn on, and this will turn on, this will turn on. After it moved the whole pixel, all of the pixels along that line will have changed state. Okay? So basically you can do, if you have a big spot and you can optimize the shape of this spot for the application, you are affecting many pixels. So you have a lot of averaging. Averaging is a magic word in sensors. It's always good. So you have a lot of averaging. B, you have a lot of pixels affected, so you can do interpolation. Or basically you have resolution. And number C, which is very, very important in optical sensors, you have dust immunity. Because if you have one piece of dust here, it will only affect 1 pixel. Since hundreds of pixels are being flipped, you wouldn't see the dust. Okay? Now if you have a very small spot, if you go to the other approach, when you have a very small spot like 1 pixel and you try to track it, when that spot hits a piece of dust, you get a huge error. Okay? So there are 3 reasons why you always use a large optical spot in optical sensing. It's the averaging, resolution, and dust. Now, this explanation is also true for non-camera sensors. Let's say you have a sensor which is a classic split detector. You have a classic split detector and you take the difference between these 2 diodes into an op-amp. Okay, like I showed you in the demo. So even in this one, and if you wanted to measure a very small movement, you would think that if you had a very small spot, it will be very sensitive to small movement. And that's incorrect. If you have a bigger spot, it's actually it's better, because what you are measuring is the difference between the 2. Okay? So if you have here a small spot, the problems you have is dust, like before. Another big problem, which I mentioned, and let's see if somebody can remember. If you have a lot of intensity in a small spot, you have a different problem in these sensors. Very good, saturation. Because remember, these things can only take about 100 milliwatt per square centimeter. It's a kind of a good number. So a sensor, square centimeter, so if you take the laser, which is a milliwatt, and you focus in the tiny spot, for sure it's a saturate. So the sensor wouldn't work. It doesn't matter where the spot is here, it'll read the same. Okay? So A, you want a big spot because of A, dust, protection, B, saturation, which is not a problem here. It could be a problem here too, but we said if it's a binary camera, we didn't care about saturation. Remember, in this example, I said the camera is binary, so saturation didn't matter. So, dust, saturation, and there is always some irregularity of the edge, irregularity of the spot. So if the spot is big, it averages. So we're getting back to the averaging business. So even if it's not a camera, even if it's a single split detector, it's always better to use a big spot. Shouldn't be too big because you want it to allow room to move, so say half the detector size or something like this. Okay, good. Now, okay, let's erase this. In all the short questions, you are supposed to answer just in 1 sentence, but you have to think it through. There is no point starting to write an essay, but you have to think the sentence through, what to say that it's clear. So say if I said which spot is better to use, so you say large spot because you can do average, interpolation, and dust immunity. And that's the answer. Don't start telling a whole story. It has to be like 1 or 2 lines. Good. Now another thing I want to point out to you about the exam is 2.5 hours, while actually you can easily do it in an hour, because you can answer each question like this in a minute, and the design problem you can do in half an hour. Now the reason why you're given 2.5 hours, so you can do a very nice job, so you're not under time pressure. So somehow, I notice most of you when you submit sketches, the sketches are really messy. They're written, crossed out, erased, overwritten. You are losing points inadvertently because of that, because I not always can read what you even wrote. There is many misunderstandings if a sketch is scribbled and messed, and I really don't understand what you mean. So since you are given for this exam at least twice of the time it takes to do, so just think everything through, write in beautiful handwriting, write very clear and concise answers. Okay, don't try to dump everything you know about the subject, just answer the question. Just like in court. Okay, you are asked which is better, say this is better because of A, B, and C. Don't don't write the whole theory of the sensor, I already know it. Okay, so just answer the question, okay? And take your time to write very clear, and especially the sketches, because let me have a sample here what you did. Because on the design problem, the sketch is a big part of the mark, right? To see, yeah, okay, here's a fellow did well. Let's look some others. But in general, don't make messy sketches with a lot of things crossed out. If you need to, just take the page out, tear the page out, make a new sketch, because you really have plenty of time. And the whole exam, properly done, should be 2 to 3 pages. If your exam is like 5 pages, you're doing something wrong, because all the questions cannot take more than 1 or 1.5 pages. Right? There's only 6 questions. You only have to write 1 sentence on each. So you couldn't really spend more than at the most 1.5 pages, and the whole design shouldn't really take more than 2 pages. 1 page is a detailed sketch, and 1 page is a selection criteria. So if you find yourself writing more than 3 pages, you're doing something wrong. You're not answering the questions. So just you have lots of time, think it through, take some piece of paper before filling out the real exam. Just draw the sketch on some scrap paper at the back of the book, of the exam book. Just sketch it a few times until it's very clear, and then make a beautiful sketch and some text to go with it. In other words, most of you, I noticed in the previous exams, you are drawing and thinking at the same time. So you're drawing something, crossing it out, drawing something else. So your whole thought process is kind of, don't do that. Just take a proof paper, make a drawing, refine it, think it through, and then put it in a final form. We'll get to it in a minute when we talk about the design problem. Okay, so when tracking light spot, good. Now 6, why do almost all power tools use a universal series wound motor? List 2 reasons. So we went through it many times. The first reason why power tools use universal, because it can run on AC. It can run actually on DC and AC, but in power tools the main thing is to have a cheap motor which can run on AC and has a very good torque speed characteristics. The universal motor has the ideal characteristics, because if we draw torque versus omega, or omega versus torque, it has this omega times T is roughly constant, which is as if it had an automatic transmission. We went through it many times. So in a power tool, if you don't want a gearbox, when you load the power tool a lot, you want a high torque and low speed. And when you do light work, you want a high speed and low torque. So when you drill with a small size drill, the drill is supposed to turn fast. So you want to work here. When you drill with a big size drill, even if you had enough torque, you really want to slow down, because otherwise the material will burn, right? Because a big size drill also has to turn slower. So it's not just that you don't have enough torque, you actually want it to go slower. So if you use a universal motor, then you have, okay, so if you had to answer this question the way I want you to answer, you say 1, ideal torque omega curve, reason number 1. Reason number 2, can work on AC operation. Okay, number 3, because it doesn't have a permanent magnet, it doesn't have to be sealed. So that's a huge factor. We talked about it a lot. And because it doesn't have to be sealed, you can blow a lot of air through the motor and make the motor much smaller, in other words much cheaper. Because any motor you can blow a lot of air through it can be made with thinner wire, with smaller, because the airflow will cool it. So cooling, no PM. Okay, so it's already 3 good reasons, okay? And there's a few other reasons which actually we didn't talk in class. Because this motor is both DC and AC, you can do easy speed control. Because the way it's done in power tools, a lot of power tools have variable speed. Because it's a DC motor, you can do speed control simply by changing the voltage. Like in a synchronous motor, to do speed control, you'd need a VFD, variable frequency drive. But because this is a DC motor, you can do easy speed control, easy reversal. Easy reversal is probably easy in most motors, but here you can do easy speed control, you just change the DC. So inside a lot of these power tools, the motor in some of them is run on DC, because what you do, you rectify the line, but you rectify it with an SCR. So we didn't get into it in the course, but I'm just telling you now, an SCR is something which if you take the sine wave, you can do a few things. You can do either an SCR or a triac. In an SCR you rectify the sine wave, but you can turn on the SCR just as a fraction of the sine wave. So you only get this part of the sine wave, and you can move where this ignition point is of the SCR, so change the average voltage. So that's how you do speed control. And you can also use a triac, which is the same thing, which is two SCRs back to back. So if this is a sine wave, you can turn it on here, and then here you can turn it on here, and you can turn it on here and turn it on here. So this is the active part. So what you're doing, you're chopping the sine wave by turning on a semiconductor switch at a certain part of the sine wave, so you can change the average value of the sine wave by where you trigger it on, and that's how all dimmers work. Like at home when you have light dimmers, they work like this. I didn't mention it in the course because it wasn't important, but since we are talking about advantages with this motor is very easy to control the speed using an SCR or a triac just by changing the average value of the voltage. Okay, so basically the answer to this question should look like this: 1, 2, 3, 4, and not the life story of Faraday, how he thought of the motor. And okay, good. Okay, so now we're getting to the design question. Okay, are you familiar with these terms? Are you familiar with SCR, triacs, and things like this? You can live a happy and meaningful life without them, so that's okay. So let's forget about it. Okay, good. Okay, so in the yes, please.
What was the second part of the question, sir?
Oh yeah, that's good. Thank you for reminding me. Okay, why does a home fridge use an induction motor? Okay, so we said many times that the DC motor is perfect in every way, but has one nasty problem, which is sparking. Oh, you learned something. Okay, good. So in a fridge, the motor has to run day and night, so the brushes will wear out. Besides sparking, which will interfere with all your smartphones. But the main problem is it has to run continuously, and the brushes have some life. The life is not bad. The life is of brushes in a motor, say 2,000 hours, typically. But in a fridge, 2,000 hours, that's only a few months. Like a year is 10,000 hours. In an electric drill, 2,000 hours is more than your lifetime. Because think of it, electric drill, you maybe use it twice a week to drill 2 holes, which take 2 minutes. So if you calculate 2,000 hours, it's more than your lifetime in electric drill. So in power tools, the 2,000 hours are not a limitation. Even in a vacuum cleaner, which is used maybe an hour a week, 2,000 hours is 40 years, right? Think of it, if it's a vacuum cleaner, which also has a universal motor in it. Okay, so an hour a week is 50 hours a year, is 40 years. 40 years you would have thrown out the vacuum cleaner for other reasons. Okay, so anyway, so bottom line is that in things like power tools, home appliances, the brush life is not a problem. But in something like a fridge, which has to run day and night, the brush life is a problem. So that's why continuous running appliances never use DC motors, because of the wear. The arcing, the RFI, is a secondary consideration, because you can say the vacuum cleaner also interferes with wireless when I run the vacuum. But somehow it's self-regulating because the vacuum cleaner is noisy enough, you can't speak on your smartphone anyway, so somehow it's not a problem, because very few people drill a hole and speak on their smartphone at the same time, but many people have the fridge working and they speak on the smartphone, so the interference comes at a different time. Interference falls off very fast with distance, so if your neighbor is vacuuming, it doesn't interfere with your wireless Wi-Fi, because it falls off at least a square root of distance, or a square of distance, a lot of times a cube of distance, right? If you want to know why, think of the electric field of a dipole, right, which falls off as a cube. So basically, it's the big concern is electrical interference within a few meters. In the next house, if they use a motor, a DC motor, your wireless stuff will not see the interference, unless it's an industrial motor, big industrial motor of 1,000 amps, and that's why in industries they don't use DC motors. Okay. Okay. So now let's approach the design problem. So first of all, in the design problems, there is many possible designs for each question, and any logical design you submit will get full credit, even if maybe it's not the most practical one. Yes?
For the design problem, it said scan a lot, but at the beginning it said laser welder.
Yeah, yeah.
Or a scanner?
No, it's a laser welder which has to scan a surface. This doesn't matter. I mean, just you can say laser. Cross out the word. Cross out the. I agree that the word welder is confusing, because usually a welder doesn't scan. Usually a welder goes in a random point to point. There are welders which scan, okay, but there are welders which are used to surfacing, like when you do a hard surfacing with a laser or surface hardening with a laser. So the laser welder is actually scanning, because it has to cover the whole surface. But really it's irrelevant here. So just think of it as a laser, not a laser welder. But all what you have to design here is a scanning system. Okay. So this is very, very similar to the problem we analyzed on last Thursday. Last Thursday we just took a spray painter, but it doesn't really matter if it's a spray painter or a welder or a laser. The whole problem was just a servo system. So you just had to estimate the bandwidth requirement, the accuracy requirement. So it doesn't really matter what it's used for. But this one, I picked a laser because it gives you a degree of freedom. If you have a spray gun, you actually have to move the spray gun, like last week. But if you have a laser, you don't actually have to move the laser. You can just move the light. So the obvious thought is, I don't need to move the laser, I can move the light. And for those who may have missed it, it even says here that you can use mirrors, just to be absolutely sure you don't move the laser, because a laser is big and heavy. Okay, so you don't want to move the laser, you want to move the light, but in moving the light, there's many, many options. So before you answer the question, especially before you start making messy sketches, okay, you think about a few concepts and do all this on a piece of scrap paper at the back of the exam paper, and only when you come up with a nice clean concept then you start answering the question. So there is a few things I want to answer this question, but I want to combine the answer with a tutorial on system design, because we still haven't finished system design. So I'll take more time than needed to answer the question in order to explain approach to system design. So there is several guidelines in system design. The first guideline is, if it's a slow system, it doesn't really matter how you do it. If you have something which has to move from A to B very slow, you can use stepper motors, lead screws, belts, DC motors, doesn't matter. If the specs become tight, if a system has to scan very fast, at some point there is preference to rotary solutions instead of solutions which go back and forth. And that's quite obvious why, right? Because if you have a fast scanner which goes back and forth, there is recoil. It comes to the end, it has to reverse. It has to reverse, there is momentum. And the momentum reverses, the whole frame receives the opposite momentum. Okay? So because of considerations of momentum, vibration, and lost time. When you reverse, you also lose time, although you may lose time in rotary scanning too. So if a system is very fast, you always start thinking, can I do it as a continuous motion? If you can't, you can go back and forth. Now that is actually a very, very important decision in all designs, and the textbook answer is always there. Everything which could be done in a rotary motion is always better than back and forth. But the practical answer is different because there are cost constraints. For example, everybody knew that if you make a car engine rotary, in theory it would be better. Instead of these pistons jumping up and down, causing imbalance, it would be much better to make a car engine rotary, but actually nobody succeeded after 100 years in making a good one. The closest one was the Wankel engine. And there are some cars with a Wankel engine and it didn't succeed. Because the problem was, it turned out that the difficulty in a rotary car engine was the seal, because it had to be variable volume in order to expand and compress, and it was very difficult to make the seal. Otherwise the geometry is very simple. It's very easy to come up with a geometry which rotates instead of having pistons, and the volume expands and shrinks. I think the same is true for a steam engine. So this is a digression from this question, but it's part of the subject of today's lecture, which is system design. So you always try to do a rotary solution, but sometimes it just doesn't work out. Like, I don't know if you know, when James Watt did the original steam engine, so the original steam engine, of course, had a piston, actually was a beam engine. It was a beam engine and piston went up and down. James Watt already understood that this is not the right solution. The right solution is a rotary steam engine. And James Watt drew this kind of engine. You have a shaft here, and you have a flap, and the steam comes in here. Steam comes in here, okay? And you have another flap here on a hinge, like this, with a stop, okay? Actually, I should draw it the other way, like this. So what happens, the steam comes in here, and let's say that this cannot be pushed. This is stationary, so as the steam expands, it's pushing this away. Okay? So it's pushing this away, so this thing is turning because this is fixed. Should draw it the other way. This was on this side. This was on this side. Had a pivot here and had a block here, or something here which stopped it from going this way. So to draw it, I'll just draw it a bit bigger so it'll be easier to see. It had a hinge here, had a pocket here, and had something here which blocked it. So the steam was coming in both directions, but the steam pushed on this but couldn't bend it backwards because it was blocked. So this was hollow. That's the best way to draw it, like this. So the steam pushed here but couldn't turn it, so it ended up pushing this part, and this part rotated. Now as this part reached here, this rotating part hit the flap, but the flap couldn't go this way but could easily go this way. So when this rotating part came this way, it pushed the flap into this pocket. There was some recess here that the flap can fold into. Then this part crossed it out of momentum. And once it crossed it, this fell back in place and the cycle repeated. Okay? Is that clear to everybody how it worked? So my hand is a flap and this is a moving part. So the moving part came all the way around, hit the flap, pushed it in the pocket, out of inertia continued up to here, the steam kept coming in. I should have drawn the steam coming here, which would have been more accurate. So the steam would come here, the flap fell back, and it kept rotating. Again, it went over this, so it kept rotating. So even in 1760, 65, when James Watt did this, he understood it's a mistake. He understood the correct engine would be rotary, like this, but he couldn't make it. And today, 200 years later, nobody could make it. Okay? Because here you have lots of problems with sealing, with materials, with a sudden movement. And as you know, in the history, same as the history of the car engine, so in the history of steam engine, there were hundreds of designs to solve this problem, and none of them commercially successful. And there are very clever designs which I don't have time to show you, because this is pretty primitive, that the flap has to jump. But there were some really clever designs how to do that without anything having to jump. None of them successful. And same in car engines. So in spite of what I said, that you always, if something has to move fast, you always try to design it rotary. Sometimes you just can't. It doesn't work. You try, it doesn't work, and it has to stay reciprocating. But in a lot of electrical things, it's easy. It's very easy to make all electric motors rotate. Okay? By the way, the very first electric motors, some people built them like steam engines. They just put a coil here, and the coil moved the piston instead of the steam, because their mindset was a mindset of pistons and engines. Okay? Okay, so all this long introduction was to tell you that when you look at the design problem, if the design problem asks for very high speed operation, you say maybe I should find a rotary solution. If there is no rotary solution, I'm back to a scanning back and forth solution. Okay? So now let's look at this design problem in this slide and come up with several solutions, some rotary, some linear, and then pick the best. So because I'm allowed to use mirrors, I can do two things. I can take the laser and I can have a moving mirror in one direction. So this is a scan. I have 100 scan lines. This is 400 millimeter. This is 100 lines, say times 1 millimeter. Okay? So the first thing I can do is I can make an assembly which has a mirror this way and has a laser, and that mirror moves back and forth. Okay? And the whole assembly is also sliding down, and I can also do it in the other direction. So one approach, which is quite simple, is, and I can do it with the whole assembly moving, or I can do it with two moving mirrors, but in general one solution would be completely rectilinear, a mirror moving back and forth this way, and the whole assembly moving this way, or maybe another mirror. So let me show you how that's done. So there's many solutions. First I calculate the bandwidth I need. So I have 10 seconds for 100 lines. So I have 100 millisecond per line. Oh, sorry, 1,000 lines? Yeah. What does it say? Okay. Oh yeah, 1,000 lines. Okay, so I'll change it. So now I have 1,000 lines times 0.1 millimeter. So now I have 10 milliseconds per line. Sorry, I misread that. Okay. So now 10 milliseconds per line. So rectilinear becomes borderline, but still doable. For example, if I have two motors, or two pulleys, and I put a timing belt, or any belt between two pulleys, okay, and I put a mirror like this connected to the timing belt, and to get better duty cycle, I should actually have two mirrors. You'll see why. So now, if the laser is coming here, it's being reflected by the mirror. Now, this has 10 milliseconds to go one way, and then the second mirror is coming in, because I don't want to waste the time, right? So I want to have two mirrors. When this mirror reaches the end of travel, the second mirror here is coming in. Okay, so except for some dead time here, I always have one mirror in the beam. Okay, I'm not saying that's the right solution. I just want to show you different solutions. So if I do that, and things like this exist, things like this, imagine if you have a bicycle chain here, like on your bicycle, and the mirror is mounted on two pins of one link of the chain. So one link of the bicycle chain has a mirror mounted to it. So this mirror will actually be able to travel around the sprocket just like your bicycle chain, because you have the links here, and the mirror will be able to travel around here, around the sprocket and scan. So it's not that difficult, because in this case, if you have like two mirrors like this, and let's say if one rotation of the wheel is 10 milliseconds, it's still reasonable. Okay, it's only a few thousand RPM, you can do it. But it's not so elegant. It's continuous. You couldn't do it back and forth, because back and forth would be too much acceleration, but you can do it continuous rectilinear. And then you have a similar scan on this side. Now this side is slow, right? On this side you can do like a mirror and on a lead screw. You can do a mirror on a lead screw with a stepper. So the laser is first hitting this mirror, which is sitting on a lead screw, then hitting this mirror, okay? And this mirror is wide. This mirror is wide, it can stick out 100 millimeter, or this whole assembly is traveling. But it's borderline. The whole thing is borderline. I'm not saying that's a good solution. I just show you a rectilinear solution. So obviously you look at that, say, the whole thing is borderline. The belt has to move too fast, mirrors to move too fast, it's not good. Okay, so the next thing you say, what about if I do it with tilting mirrors? Because this is after all light, and the closer I go to rotary, the better. So this is fully rectilinear, but what I can do is I can take a stepper motor or a motor, and we'll calculate which motor in a moment. I can put a mirror on it, so this is a laser. Okay, and then I can scan, okay, by tilting this mirror, I can scan the beam, say over a reasonable angle. Let's say I scan it over 45 degrees. Now I have a long mirror here, okay, which is directing the beam down into the blackboard. So I have one mirror which directs the beam to any place here. Now this thing, looking from the side, it looks like this. This is this. Now the light comes down in a fan like this and gets bounced off here, okay, but this mirror can tilt and bring the light across a 100 millimeter area. So this is my scanned area, okay. The top mirror brings the light to any position in X I want, and this whole mirror is tilting and bringing the light to any position in Y I want. Is that clear? Good. Okay, so I'll draw it in 3D just so it's completely clear. So this is the laser beam coming in. It's hitting a first mirror, which is connected to a motor, and in a moment we'll calculate which motor. Now, this first mirror is bringing the light down, and it's hitting a second mirror, and the second mirror is also connected on a motor. We'll calculate in a moment which motor. So this can bring it anywhere, and the second mirror brings the light in this plane to anywhere I want on this page. Now this looks like a much better solution than a rectilinear solution for many reasons. First of all, it's rotary, and we always said rotary is better than linear. B, the movements are small because you gain from the fact that it multiplies. If this moves theta, the light is being moved to theta, so you don't really need much. If you wanted to scan this at 90 degrees, this only has to move 45 degrees. Okay? So you can do that, and then if the speeds come out too fast, then you can do something else, like that this thing can be rotating continuously, and that's a solution they have in laser printers. Because this problem is a bit similar to a laser printer, but in a laser printer you don't use a second mirror. What you do is just move the page. Like in this assignment, it implied that you can't move the workpiece or the laser. It implied you have to move the light. But if this was a laser printer, all what you need is this mirror is fixed, and you just slide the page. And that's how all laser printers work. So what they do in a laser printer, instead of scanning back and forth, because it is scanning, what they do, they have a polygon. Polygon is a thing like this where the sides are mirrored. And this is sitting on a motor which rotates continuously. Now, you hit it with this, and as it rotates, it deflects the beam from here to here to here to here to here. And then when it finishes, the next facet comes in. So there is very little dead space. The dead space is when the beam is sitting on two facets of the polygon. So if I draw it, this is a polygon. Say this is the beam, hitting here and being reflected. Now as it turns, at some point, the beam is hitting on two facets of the polygon, so one part is going this way, one part is going that way, so you make sure that this part happens outside the scan area, or you shut off the beam. The assumption is the laser can be turned on or off, so you shut off the beam here, so you only have the beam on when it's fully on the mirror. Okay, so this is called a polygon scanner. And that is the most common type of optical scanner. They come with 6, with 5, with 9, with 10, with any number of facets you want, depending on the system design. So there is no difference between this and this, except that here the mirror has to go back and forth. And at some speed, the mirror is just not fast enough to go back and forth, and then you have to use a polygon, because a polygon keeps going in one direction. By the way, you can do a mirror. If you didn't think of a polygon, you could have said this motor goes in one direction, so the scan is only in one direction, right? And that's why the question said you can choose unidirectional or bidirectional, because this can rock back and forth and have bidirectional scan. If you didn't think about it, just make it go in one direction, and then the only problem is you have a loss of duty cycle. Because you scan, and then you have to wait a long time till the mirror comes back. Right? Because if this only turns 45 degrees to do the scan, you have to wait 315 degrees. So 7/8 of the time you have no light. Right? Because you can't really use a scan much bigger than 90. I mean, you can, but if you draw it, you'll see the problems. If you want to use a scan angle of almost 180, the beam will spread over the whole mirror. So for practical reasons, you can't really use, in theory, a 90-degree scan of a mirror will give you a 180-degree scan of the light, but it's at the limits, the geometry is awkward. So a more reasonable number is, say, 45-degree scan, but which give you 90. But if this goes 45 degrees and then has to turn around all the way and come back, 315 out of 360, it's not used. So the utilization or duty cycle is poor, right? It's 1/8, because only 45 degree out of 360 are active. Now if you think of it, you say, okay, maybe I should make the mirror mirrored on both sides, which is easy. So when it comes around 180, you get another scan. And this improves this number to 1/4, and then it's already more reasonable. And if you know a bit more about these things, you say, why don't I put in a polygon, and then I have almost 100% utilization. But you didn't have to know about that. You could have just said, I take a mirror and make it rotate. So the steps kind of progression is from a rectilinear system, which is very borderline in this case, but still can be done, to a reversing system, and we'll calculate in a moment the bandwidth we need and all this, to a continuous system, which is always the best. Okay? And it's best to do it like with tilting mirrors rather than rectilinear, of course. So now let's look at the spec. So we have 10 milliseconds per line. Now we also have to assume there is always time lost. Right? Even if you do a polygon like this, there is time lost because here at the ends the beam cannot be used, so net we don't really have 10 milliseconds per line. So because there's time lost at the end, let's say we have 8 milliseconds per line. Okay? So in this axis it's quite clear we can use a stepper motor. And the reason I think it's quite clear because this axis is very slow. It only has to do a tilt in 10 seconds. It's much less than a rotation per second. You don't have any doubt. You can use a stepper motor. The only calculation is accuracy. Because we want, spec says 1% accuracy. So I'm assuming it applies to both directions. So if it was direct drive, and let's say this also has to go 45 degrees. Okay? So 45 degrees in a stepper without micro stepping is 1/8 of 200 steps. So it's 25 steps. Now you can micro-step it easily into as many steps as you want. So let's say if you drive it directly and this goes 45 degrees, Okay, so 45 degrees is 1/8 of a rotation. A typical stepper is 200 steps. So, and you divide that by 8. You divide that by 8, you end up with the 25 steps. So, what is an accuracy of a stepper? Clearly I can convert the 25 steps to any number of steps I want by micro stepping, but the question is accuracy. So do you remember what is an accuracy of a stepper per step, roughly?
2.5%.
How much? Yeah, the best steppers are 2%, the lousy stepper is 5%. So that's the range. So let's say even 5%, so I only have to do this times 4 to get I have to get it times 40. So since I have 1,000 lines in this direction, okay, I have to go by 40, so I have to do 40 microsteps, and my accuracy has to be 1%. So I will have, let's say, 1,000 microsteps by using a 40 microstep per step. Okay, I have 1,000 microsteps. The question is, will it be accurate to 1%? So if it's accurate to 2-3% of this, okay, of one step, so I have 40 microsteps, and the accuracy is, let's say if it's 2.5%, it's 1 times in 40, okay? So let's say 2.5%, I just picked a number, this is actually 1 part in 40. So if I have 40 microsteps, and the accuracy of the stepper is 1 part in 40, it's accurate to 1 microstep. Another way of saying it is no point to divide it into more than 40 microsteps, because 2% of that, 2.5% of that is 1 microstep, it's plus minus 1 microstep. Now what accuracy do I need in microsteps? Because I need 1% accuracy out of 1,000 microsteps. So what I need is actually plus minus 10 microsteps, that's all. Because the spec says 1% accuracy. I divided this into 1,000 microsteps. I need 1% of that, plus minus. So I actually, what it means, that I need plus minus 10 microsteps after I converted this axis to a microstepper, but the natural accuracy of the stepper direct driven is 1 microstep. So I have 10 times the accuracy I need. So on this axis, on the y-axis, I have no problem whatsoever. I just take a stepper motor, put a mirror on it, calculate the speed and accuracy, and say, yeah, check. But you have to write it. You have to write it. Speed of this is 1/4 of a rotation in, say, 10 seconds. Okay, if you do bidirectional scan, it's very, very slow. There's no speed issue. The accuracy of this is 2.5% of this, which works out to be 1 microstep. I need 10 microstep. Check, no issue. Okay, done. Yes.
Why is this slow for this?
Pardon?
Why is this slow?
Because I have 10 seconds to scan the whole area. That's what the spec says. And this is a fast axis. This is a fast axis. So the way I scan the area is like this. The fast axis goes back and forth, and the slow axis just moves slowly this way, and it has to, from here to here, it has to take 10 seconds, or a bit less. So I have lots of time for this axis, because that's a spec. To cover it from here to here, I have 10 seconds.
But I think that it can only move after you finish scanning one line, right?
No, I didn't say that. It can move while you're scanning. Who said it can only move its end? It can move while it's scanning.
Don't you have to scan in a straight line?
It will be a straight line, because if you do nothing smart, it will be like this. The lines will be slanted, but they will be slanted 1/1000th of the size. Okay? Let's say you scan with a polygon and it's moving while it's scanning. So each line will be slanted like this. Okay? Now, first of all, it's within the accuracy. The accuracy was 10 lines. So the first answer, it's completely within the accuracy, ignore it. The second answer is you can tilt. You can take this whole scanning assembly and tilt it a little bit, and then all the lines will now be parallel. Okay? And the third answer is, if you actually do the calculation, you see that this length will not be one line, but 1/8 of a line. And the reason for that, and that takes a minute of thinking, there is a duty cycle involved. So it depends. If you use a single mirror, this single mirror goes much faster than the one scan line because only 1/8 of it is used. So this mirror does one scan line worth, or one scan line delay in one rotation, but out of this only 1/8 is used. So if I use a rotating single mirror, that slope will actually be 1/8 of a scan line. Anyway, you can think later about it, but I already gave you 2 reasons why it's not a problem. So I don't have to get into the third reason. So it's not a problem, A, because that is 10 times smaller error than the accuracy. B, I can tilt the whole scanner and make it straight. Okay? So it's not an issue. But you have to say that. You have to say this will produce scan lines, but this is less than 1% error, so I ignore the tilt. Or okay, so now we have some messy design, and now we are going, so this is all the sketches and calculations you do at the back before you start writing one word of the answer. Okay. Then you say, okay, we are going to draw, let's do a quick estimate on this and decide if it can be a mirror which rocks or does it have to be a mirror which rotates, and then we know the answer, and then we do a clean solution. So I have, for a scan line, I have 8 milliseconds. Okay, so can I do it rocking back and forth? Okay, not really, but I should put down some numbers. Okay, so what is the stepping rate of a stepper motor? Or let's do it a different way to make it even simpler. This has to go an eighth of a rotation in 8 milliseconds. Because if we do a simple scanning, it's an eighth of a rotation, roughly. So it has to go an eighth of a rotation in 8 milliseconds. So it can do a full rotation. No. It has actually, no, it's worse than that. It has to come back and be, yeah, no, if I do bidirectional, it's correct. It has 8 milliseconds to do this, 8 milliseconds to do that. So it's an eighth of a rotation, 8 milliseconds. So this is equivalent of one rotation in 64 milliseconds. Okay? So how many RPM is that? Just kind of for a ballpark, okay? So this is 900 RPM. Because I know that 16 milliseconds is one cycle of the power line, right? 60 hertz is 16 milliseconds, and I know the synchronous speed of the power line is 3600. So I don't have to calculate, because this is 4 sine waves of the power line. So I don't need to calculate. I know this will be 900 RPM. So 900 RPM is borderline for a stepper to do. Because a stepper can actually do that, but you have to ramp up a bit at the beginning, ramp up at the end. When I gave you guidelines for steppers, I said a stepper can do a few hundred RPM. And in terms of step rate, I said roughly 1,000 steps per second. 1,000 steps per second is 5 RPS. So that's a good number, like a guideline. And 5 RPS is 300 RPM. So 900 is pushing it. But one thing you have to think of, whenever you try to match a motor to a target, you can always use gearing. So let's say it's not fast enough for a stepper, but maybe that stepper has much more resolution than you need. So you can always trade speed for resolution or speed for torque. In other words, neither this stepper nor this stepper has to be direct drive. You can always gear it down. And that's the important point to understand here, that if it doesn't work out, you say, well, let's just check for a minute. If I have much more resolution than I need, I can gear it down with a 3-to-1, 4-to-1 gear. So I can take the stepper motor, and I can put the mirror, I can put a timing belt. So this is a stepper motor, I can speed it up 3-to-1, and this is a mirror. And this stepper will have to move, instead of 45 degrees, just 15 degrees. Okay? And now I'll have enough speed. But will I have enough accuracy? So does everybody understand that if you have overkill in one axis and you don't achieve the other axis, maybe you should gear the stepper. And that's the same for any motor. But it's still marginal. All the things you do in your head quickly, because you can see it's all leading towards a polygon or rotating mirror, but you have to do quickly in your head a calculation. But the problem is that now this is only about 10 steps, okay? Because one step in a stepper is 1.8 degrees. So 15 degrees, including the reversals and everything, is 10 steps. Now, I have enough time to do it, because I have 10 steps, I have about 10 milliseconds, I have enough time to do it, but what about accuracy? Now, the accuracy is 2% of steps, so let's say 1 part in 50 at the best, so that accuracy is 1 part in 500. Because each step, each one of these steps at the 2% stepper, which is the best stepper, is 1 part in 50 accuracy times 10 steps. So the overall error is 1 part in 500, because it's 1 part in 50 of one step, but I have 10 steps. So 1 part in 500 is marginal, because the scan is 400 millimeter. Accuracy of the best stepper is 1 part in 500, which means 0.8 millimeter. So I can see the whole thing is marginal. Surprisingly, it is just doable. If you gear down the stepper 3 to 1, pick the 2% stepper, the numbers just work out for a mirror which goes back and forth. But you can see it's going to be a design which is cramped. Yes?
Why do we decide to use steppers from the beginning? Why is that our first?
Very good question. Because the simplest servo is a stepper. So you always start with a stepper. It's the cheapest, the simplest. It doesn't need an encoder, doesn't need sensors. It's always the simplest. Okay? But for things like this, not for moving, wind generators or ships, but for simple.
Like a moving coil, just back and forth.
You can do that too, but then you need an encoder, then you have to explain which encoder you use. So if you want to save time, if a stepper fits, you say, I'll use a stepper, then you don't have to explain anything else. If you're moving coil, you have to say, okay, which encoder, which moving coil, how big. But in theory, yes, you could do this with moving coil, moving magnet. You can do it with anything. As I said, I'm not judging the solution by, is it elegant? I'm just judging it, does it work? So any one of the solutions will give them full credit if you can show it works. So all what I'm leading you through the stepper calculation, because here it probably doesn't make sense to use a stepper, but I want to make sure you know how to calculate it with a stepper. Okay? So you remember you can always gear the stepper, and then you can make it just work, but it's not elegant. Yes, so you had a question here?
Just that, won't the belt reduce your accuracy a bit too?
No, it turns out not, which is very surprising because of the magic word. You know what the magic word is? Averaging. Because the belt has many teeth, so it turns out because of the many teeth, let's say if this has 60 teeth, this has 20 teeth, it will be accurate to an astonishing degree. In the old days when I was involved in the printing industry, we built machines which were accurate to 0.1 micron. To write lines with laser with 0.1 micron placement. So we did a lot of tests of timing belts because we wanted to do this kind of thing. And there was never an error traceable to the timing belt, which is amazing. There was errors traceable to the bearings, to the lead screws, but never to the timing belts. Okay, so yes?
With this question, if you wanted to use an encoder, what's the work that you have to show?
Pardon?
If we use an encoder like you said.
So you have to say if you use a moving coil, you have to say use encoder, you have to say how many lines of the encoder, you have to write a few more sentences. But it's completely legitimate. You can skip this whole discussion here by saying I'll use a moving coil actuator or moving magnet actuator with an encoder, but you have to specify the number of lines, because if this has to write, if this has to do 400 or whatever number of spots, you have to make sure the encoder has enough lines over an eighth of a turn to have enough points. At least it has to have 800 lines, because this is 1/8 of a rotation, and within the eighth of a rotation you have to be within 1%. So 1% is 100 lines minimum, so the encoder has to be minimum 800 lines. but you have to show that.
What's only doing
Pardon? In other words, if you
100 lines across the rotation, I mean, it doesn't have to be a full.
no, it has to have, but encoders are full circles, right? So you buy them as full circles. You have to say, I can use a moving coil, moving magnet with an encoder, but the encoder has to be 800 lines, otherwise it can't get 1%. Okay, or you can use a polygon. Okay, and you can do that. You can use a synchronous motor, and then the speed is constant, and then you have an encoder here to know your position. So, yes.
Total distance of 1,000 millimeters.
Okay, there is some other issues here I don't have time to cover, because you may be tempted to say, I can use very small movements, I can use some special actuator with very small movements and very small angles, but then the total distances will become big. Okay, so I wanted another constraint, that the thing has to be compact, because otherwise you may write some answers. I'll put a piezo under the mirror, put the mirror here, I'll move the mirror half a degree, and then it'll give me a very nice linear scan 10 meters away. So I wanted to weed out all the solutions which are not practical because they'll use huge distances. Okay, so then I put a constraint that the total optical path meaning from here to here to here to here, this has to be less than a meter. So just a constraints to weed out in practical designs. Yes?
Is it practical then that you'd have 1,000 line scan with an error that's much less than, like, well, it's about 10 full scans?
Yeah,
That is reasonable.
it depends on the spec. Certainly if this was for welding where the laser spot is big and the scans overlap, yes. I mean, it's just a made-up spec. If it's practical or not, it depends on application. If this was a painting robot, for sure. If this was a welding, yes. If this was a cutting, no. It depends on the application, but it doesn't matter. The question is a made-up question. All that you have to show that you understood how to solve the spec. Yeah.
Why is mentioned that starting to begin at a random access?
One thing I wanted you to think of, that if you have a system like this and you turn it on, you don't know where you are. So in order to be able to start from a random position, you have to know where you are when you turn it on. So you have to add a sensor which tells you where you are. Now that's very easy here, because if it is an encoder, the encoder tells you where you are. You can use an absolute encoder, but because you have scanning light, it's very easy. You can put one long optical sensor here, like a photocell, and one little photocell here. So this long photocell gives you a pulse at the end of each scan. So you start counting from this pulse, and this photocell tells you when you reach the end of this scan. So you have to include in the design two sensors, could be mechanical, could be photocells, which tell you the ends of the scan, and then you know where you are. Yes, at the end. Well, you have to be reasonable. So again, if you say I'm going to know where I am because I'm going to have an encoder, then you have to say this encoder has to have like 1,000 lines, otherwise one line of the encoder is more than the error. So you know, any solution is acceptable, but you have to calculate it. If I say I know where I am because I'm going to put an absolute encoder, this absolute encoder has to have like a 10-bit encoder.
Maybe a better question.
Yeah.
If you know of a solution that's practical,
Yeah.
you know there's a sensor for it,
Yeah.
you don't know how to calculate the accuracy, so you just pick something you can calculate the accuracy that's not as good as the solution?
No, you have to show, let's say there is a system like this available, but you have to show the calculation, what accuracy you need.
That's what I mean. So just
Yeah.
pick something you can actually calculate, even if you know there's a better one available, but you can't if you don't know how to calculate.
Well, you have to calculate, then you can say this has to be 800 lines encoder, I know these exist. You don't have to say if it exists or not, but you have to calculate the spec of the sensor if you're using a sensor. Yes?
Is it reasonable just to say the position stored in memory, or not?
Pardon?
With a stepper, you could just store the position in memory, you know, on the computer.
No, that's not an answer, because when you power off, somebody can push it and it can move in shipping. When you power it on again, you don't know where you are. You can't store the position in memory because there's nothing stopping it at this position. right? If you pushed it, you lost the position, and then it hits the limit. Then it's gone forever. Yeah, so it has to be practical. Okay, so this is just a guideline. So the correct solution here, the most elegant solution, would have been a polygon with a stepper motor for the other axis. Okay, guys, see you on the 23rd. Thank you very much. Good.